over the past few months, our team has designed a chemical process to produce dimethyl ether as a friendly environmental alternative for diesel fuel. I'm Vance Pryzybys.
I'm John Brezovec.
I'm Mickonis.
And I'm Marissa Maney, and we are Team DARTH Vapor.
So, kind of the course outline of our presentation. First, we're going to talk about our general plant info, like the location, capacity, and then the specifications used to design our plant. We'll then be getting into the process overview of our design, the economics involved, and lastly, we'll be providing recommendations for moving forward. The DME plant location is expected to be built in our company's existing Gulf Coast complex. As of now, we are looking at July of 2023 as our startup. Our plant will be utilizing a low-quality methanol feed to produce DME, and we will be running with an operating time of 8,400 hours per year. So our team was given the task to design a process to produce 53,600 pounds per hour of DME with a minimum purity requirement of 98.5%. The input to our process is 88,501 pounds per hour, and this is of low-quality methanol, meaning that our stream is 90% methanol, 2% water, 3% acetone, 5% ethanol, and then 0.5 milligrams per kilogram are chloride ions. So our team was successfully able to meet this goal of producing 53,600 pounds per hour of DME with a purity of 98.8%. This includes the lubricant additive that is required for DME to match the natural lubricity of diesel fuel. So the reaction to produce DME is a dehydration reaction. So two methanols are going to undergo this dehydration reaction to produce DME in water. Our team decided to use the gamma aluminum oxide catalyst, and this is under high temperature conditions. Our team felt that this catalyst would work best for our process because it's well known throughout industry as being very efficient at low cost. It has a high DME selectivity and an overall long lifetime for the catalyst. Our team also in our process purified a side product, methyl ethyl ether, ME, and this also undergoes a dehydration reaction between methanol and ethanol. Two other side products that were formed are diethyl ether, which is a dehydration reaction of two ethanols, and acetaldehyde, which is a reaction involving acetone. However, these were not considered in our process for purifying. Or they were considered, but we did not purify those. So when producing our plant, we had to ensure that our DME would not violate the Department of Transportation DME fuel standards. So these standards require that DME is 98.5% pure, methanol max concentration of 0.05%, water 0.03%, and sulfur 3 milligrams per kilogram. So as you can see from our production results, our DME met the spec at 98.8%, as well as no methanol, water, or sulfur in this stream. In order to sell MEE as a product, we had to ensure that it was at least 99.8% pure. And as you can see, we met this spec right on the dot at 99.8% purity. I'm now going to pass it over to Aaron, and he's going to discuss our plant we designed.
Thank you, Vance. So overall, our process, as previously mentioned, takes an impure methanol feed as well as a recycled methanol feed from downstream, puts it into a reactor, and then through various separation columns, where we'll eventually be able to sell the lubricated DME stream, the MEE stream, as well as a stream that contains an azeotropic mixture of acetone and methanol, and we will then send this to the liquid fuel system to power other parts of our entire design. So aside from just the raw materials of the impure methanol feed and the lubricant, we also have to take into account that the reactor is a packed bed reactor with the gamma aluminum oxide catalyst filled in, and we also have an additional stream coming out of just wastewater, which will just be sent to the wastewater treatment facility. So now we will go into further in depth on each specific larger unit operation. So coming back to the reactor, again, it's a mixture of the impure methanol feed as well as that recycled methanol as seen downstream in the process. Those both will mix together and then go into the packed bed reactor. Around the reactor, there will also be a process-to-process heat integration, which will significantly lower the utilities by having the reactor effluent heat up the inlet and simultaneously the inlet cooling down the effluent. The reactor itself will be constructed out of a chrome moly material because the chloride ions in the feed would cause stress corrosion if the reactor is made out of stainless steel, and at the high temperature carbon steel is also dangerous, so chrome moly is needed. All other process equipment such as the other columns, all of the piping, the boilers, condensers, and all the heat exchangers and pumps will all be constructed out of carbon steel, again, just to ensure that there is no chloride stress corrosion throughout the plant, and carbon steel is also cheaper than stainless steel. And finally, while the reactor is running and at steady state, there will only be one reactor in place. However, we have 2 reactors in this plant. The other reactor will be sitting idle for catalyst regeneration, and we will then just switch that over during the annual plant shutdown. So now I'm going to hand it over to John, and he's going to talk a little bit more about all the different distillation columns and the products that we're separating out of them.
All right, thanks, Aaron. So the reactor effluent is first passed to our DME separation column. We decided to separate DME first out of the effluent in order to remove the bulk of the material from the reactor effluent stream. So our distillate from this first column is almost pure DME with a little bit of MEE in it. We then mix it with our lubricant to produce our final primary revenue stream of that lubricated DME. The bottoms then are processed to recycle back to the front of the facility. It's also important to note that the bottoms have to contain less than 10 pounds per hour of DME for downstream separations to maintain and spec. This is particularly important for the MEE column. The bottoms for the first DME separation column are sent to our second distillation column, where ethers and an azeotropic acetone and methanol stream is removed in the distillate, and the bottoms are set for further separation to recycle. The third distillation column is our water removal column, where out of the bottoms we get a wastewater stream that contains some methanol, which we send to the wastewater treatment facility. Off the top in the distillate, we have our methanol with a little bit of ethanol and acetone in it that we send back to the front of the process to form more DME and MEE. The tops of the second column are then sent to our fourth and final distillation column in our base case. This column separates our MEE and distillate, which we sell as an additional revenue stream. And then off the bottom, we have azeotropic acetone and methanol, as well as the DEE, which we use, as Aaron said, as liquid fuel to power our facility. In addition to the base case, we also considered one major alternative design, which we modeled as well. This is to take the liquid fuel stream off the bottom of our last base case distillation column and send it to a set of distillation columns which separates the acetone from that stream. The first one is a low pressure column, and out of this column we have a low pressure azeotrope off the top of methanol and acetone, and off the bottom we have a stream that is mostly methanol that we could potentially send back to the front of the process for recycle. We did not model this part of the design because it required that upstream equipment would need to be remodeled. The tops of this first low pressure column are then sent to the high pressure column, which produces very pure acetone off the bottom that we sell again as an additional revenue stream. And then off the top we have a high pressure azeotrope of methanol and acetone, which we sell as, again, which we use as liquid fuel to power the rest of my plant. So I will now pass it over to Marissa, who will talk about the economics of the plant.
Thank you, John. So I will discuss the economic evaluation that was completed for our base case, which includes total plant costs, yearly operating and utility costs, and revenue from the sales of our products. First, our total plant cost was determined to be $24 million, where the total OBL improvement makes up 37% of this plant cost. To continue, the IBL makes up 33%, which is the equipment cost plus the equipment installation cost. Now, the equipment cost was estimated using Aspen Process Economic Analyzer, otherwise known as ICRIS. To continue, Our total plant cost will have 3% office cost, 2% from miscellaneous costs such as spare parts, 2% from startup costs, 6% from escalation, and 17% contingency. To continue, our base case operating costs were determined to be $122 million per year, where you can see that the raw materials, or our methanol feed stream, makes up 84% of these operating costs. 7% of the operating costs are utilities. Selling, general, and admission makes up 4%, labor 2%, and other costs 3%. Now I will talk more about the utility costs in our base case design. The utility costs were determined to be approximately $9 million per year, with steam making up about 50% of those costs. Medium pressure steam, specifically, makes up 32% of the costs. This is because medium pressure steam is needed to heat up the inlet to our reactor, as well as in the reboiler of our DME purification column. Low pressure steam makes up 17% of our utility costs, and low pressure steam 2%. To continue, wastewater makes up 30% of our utility costs. This is because our wastewater has a high BOD. Electricity usage is another 14%, cooling water 4%, and refrigerant 160 1%. Finally, our yearly revenue was determined to be $113 million, where our primary chemical product, DME, or dimethyl ether, makes up 86% of this revenue. Our side product, methyl ethyl ether, makes up 13%, and liquid fuel 1%. Now I will compare our base case to our alternative design, specifically the differences in cumulative cash flow and cumulative present worth. It was determined for our base case that the cumulative cash flow would be negative $171 million, and the cumulative present worth negative $59 million. Now, if we included the acetone purification columns in our alternative design, we would increase this cumulative cash flow by $53 million to negative $118 million. Similarly, our cumulative present worth would increase by $15 million to make negative $44 million cumulative present worth. So I will pass this on to Aaron to present our sensitivity analysis and some recommendations and conclusions on our chemical plant.
Thank you, Marissa. So we performed 5 sensitivity analyses to determine the limits of our profitability for our base case. And this included things like changing the methanol feedstock cost, changing the DME market price, changing the natural gas pricing, the utility costs, as well as the capital costs. However, only 2 of those sensitivity analyses really showed a large impact that could lead us to eventually reach our 15% return on investment goal that we set for ourselves. And this would be if our methanol feedstock cost reduced from 13 cents per pound to 11 cents per pound, so only 2 cents per pound cheaper, would allow us to reach our goal of 15% return on investment. Or if our DME market price increased roughly 3 cents per pound from 21.5 cents per pound to 24.3 cents per pound. So this means that overall, we cannot recommend to build the plant currently with its current design, as well as the current price of the methanol feedstock and the DME market price. However, if the methanol feedstock cost was decreased by just 16%, or the DME selling price increased by roughly 13%, then we would reach that 15% IRR goal, and we would be able to build the plant. And obviously, a combination of these factors with a lower magnitude would still allow us to reach this goal. Overall, we have to recommend the alternative design to the base case because, as we previously shown, it has a less negative cumulative cash flow and present worth. So we have to recommend using this design if either the methanol feedstock cost lowers or if the DME selling price increases. So sadly, we cannot recommend the plant, which means we will not be able to provide a more eco-friendly fuel alternative to diesel at this time. However, hopefully changes in the market will allow this plant to be built sometime in the near future, and then we'll be able to provide a cleaner diesel alternative to anyone that drives those sorts of automobiles or trucks. Thank you for listening to our presentation.